Hi, we are Team Hate You. This is our Stat 101 final project presentation. Our team planned and analyzed an experiment utilizing the data set diabetes with the goal of inferring which random forest parameters are most important, influencing cross-validate accuracy. We created to design and compare to find the best design given only 35 learns. Here we provide two design, fractionals and optimal design. For figure 1, we can see all the main effects are not aliased with any other main effect and two interaction terms, but some of two interaction terms are aliased with other interactions. For figure 2, all the main effects are two interactions are not aliased with any other terms, but many of them are partially aliased with each other. For the fractional design, there are three interaction terms that are fully aliased with the other two interaction, which means multicollinearity is violated. However, there is no multicollinearity between main effect and two interaction terms. Here, we draw a square. Unlike fractional design, the optimal design, in spite of no aliasing in this design, we see a lot of multicollinearity between main effect and two interaction terms.
We made two interaction model and produced a result of summarized of the model, and it gives us which effect is significant and which is not. We can also see that by using linear plot, which gives pretty much same result as previous slide. So based on the result we've got, we are now able to make a new reduced model, and we can get all the effects we want to know are significant. And we fit a linear regression model, including significant main effects and interaction terms. And in this slide, we need to check our assumptions. So we run the residual and normal plot. All the assumptions are satisfied here, but actually there is one outlier, but most points lie on the linear line. So our team wants to say this is okay. And for the residual plot, there are little deviation, which we believe not serious, but we will talk about that at the end of this presentation. And BIF is very good. Yeah.
To conclude, we'd like to highlight the strengths of our model. Our model provided a decently large adjusted R-squared value of 0.8729, which means 87.29% of the variability and cross-validation can be attributed to the variation in our parameters, class weight, cutoff, and max nodes, and their interactions. Our model only has 6 parameters, so it's relatively easy to digest. Finally, our parameters have very low variance inflation factors, which means there's little to no multicollinearity among our predictors. Some strengths of our fractional factorial design include the fact that it is resolution 4. This means there's no aliasing until you look at 3-factor interactions and above. We're only studying the main effects and their interactions, so there's no aliasing of our parameters of interest. Furthermore, our design is 2 to the 7 minus 2, which utilizes 32 runs. This design utilizes as many runs as possible while maintaining the fractional factorial design where the run number must be a power of 2. By using as many runs as possible, we decrease the experimental variability. However, because we were allotted money for 35 runs, we actually saved some money for the 3 runs we did not utilize. Some recommendations we would have to consider would be a more precise model in the future. We went down the inferential route for this project, but in the future, we could attempt to find a linear model that provides a better prediction for cross-validation. 87.29 is a decent correlation, but typically the threshold for good correlation is 0.9 and above. We sacrifice some precision for simplicity, so one might also consider adding more predictors to increase precision. Another recommendation to make the model stronger would be to transform the data so the residuals have a more equal dispersion pattern around the plot. As you can see in this plot, there is some skew in the residuals versus predicted plot. The last recommendation we have for our model may be to exclude the interaction terms for ease of interpretability and increased practicality. Some weaknesses of the design include the inability to estimate 2-factor interactions and higher due to aliasing. This model also does not capitalize on all 35 possible runs allotted to us like the D-optimal design could have. Thank you.
Thank you.
Thank you.